Welcome to the video lecture series for Texas A&M University course Math 152. Today we will look at section 9.4, Area of a Surface of Revolution. You can find the accompanying handouts at bit.ly/Raelene Math 152. Let's begin. As a warm-up, we are going to state the formulas for the arc length and area of a sector of a circle, given that the central angle is theta and the radius is r. So if we happen to have a circle, and we are talking about a sector of the circle where the radius of the circle is r and the central angle is theta, we can say that the arc length, often referred to as S, is equal to theta times r, and the area of the sector, A with a subscript of sector, is given by 1/2 theta times r squared. For derivation of these formulas, you can see Math 150 video or pages in section 4.1, Introduction to Trig and Right Triangle. Introduction to Angles, rather, and Right Triangle Trig. One thing to note here is that theta, the central angle, is measured in radians and not degrees. Okay, number 2, we want to determine the lateral, which means the side and not the end or the base surface area of a cone of radius A and a lateral or slant length of B. We're going to rename the radius here to be A, and the slant length is going to be renamed as B. So if we were to cut along here, we see that the cone unravels as a sector. And we have an arc length of the sector along here, which is the circumference of the base. And the circumference of the base in this case is 2 pi times the radius, and the radius is A. Similarly, the radius of the sector when we unravel it is the length B, which was the slant side. And so we want to determine the surface area of the cone, which means we want to find the area of a sector. In general, we just said that the area of a sector of central angle theta and radius r is given by 1/2 theta r squared. So we have 1/2 times the central angle, which we are still labeling as theta, times the radius of the sector, not the radius of the cone, and the radius of the sector happens to be the slant length b. So that's the lateral surface area, or simply the surface area of the surface, which is the sector of the circle. In part B, we want to find the lateral or surface area of a frustum of a cone with average radius of r and a length of L. So we see here that the frustum of a cone has a length of L, and we are going to be referring to the average radius. So we have that r1 plus r2 divided by 2 is equal to r. And therefore we could say that r1 plus r2 is equal to 2r, where r1 is the smaller radius of the frustum of the cone, and r2 is the larger radius. So later on we're going to see the average radius here is r. In the meantime, we're going to refer to the frustum as being extended to a full cone, and we're going to let the smaller cone that's missing, when we subtract the missing piece of the cone from the full cone to get just the frustum, I'm going to refer to this slant length as, I think I'm going to call it B. And so we have R1 and B are the dimensions of the small cone, and the radius of the big cone is R2, and the slant length is B plus L. So remember, our goal was to come up with the surface area of this band, of this frustum of a cone. So we know that the surface area is going to be the area of the large cone minus the area of the small or missing cone. Well, if we just go back a minute, we can make a replacement here in terms of theta. We don't want to talk about theta. And so if we don't want to talk about theta, we need to make a replacement. We know from the arc length formula, we know arc length, let me write it in terms of S. S equals theta r, and so the arc length of this sector is C, or 2 pi a, and that's equal to the central angle theta times the radius of the sector, which is b. And so we can come up with a substitution that says that theta is equal to 2 pi a divided by b. So if we substitute in here, we get that the area of the sector, which is the surface area of the cone, is going to equal 1/2 theta, which is 2 pi a divided by b, where a is the radius of the cone and b is the slant length, multiplied by b squared. So we're just taking theta and substituting it in here for the area of the sector. We can reduce, and we are left with the surface area of the cone is pi a b, where a is the radius of the cone and b is the slant length. Okay, so now coming over here, we can apply that without having to know anything about the central angle theta. The area of the large cone is going to be pi times its radius times its length, its side length. And so the large cone has a radius of r2, and it has a side length of b plus l. Minus the area of the small cone is pi times its radius, r1, times its length, or side length, which is b. And we can expand this and rearrange it a little bit. And we can collect some like terms. There are no exact like terms, but I am going to group the terms with the b common. So I'm going to get pi r squared minus, r2 minus r1, and then times b, and then plus the middle term, pi r2l. From here we go back to the instructions, which says to determine the surface area for the frustum of a cone with average radius of r and length l. So we somehow want to get rid of anything that's not r or l. Well, we don't have r at all, but we do know that r is related according to this red equation over here, and we don't want b either. So maybe we should come up with an expression or an equation to eliminate b. So what we notice is that we have similar triangles, and we know that r1 over b is going to equal the ratio of radius of the big cone over length of the big cone. And when I say length of the big cone, I mean the side length. So from those two similar triangles, knowing that we want to solve for b, we can say that b over r1 is equal to the total length, b plus l, over the big cone radius, which is r2. And from here we can rearrange to solve for b. I think I'm going to do that on the next page just because I don't want to make it really small. So b over r1 is equal to b plus l over r2, which implies that br2 is equal to br1 plus lr1. And solving for b, we can take all the b terms to one side. And therefore b is equal to lr1 divided by r2 minus r1. So we can take that and substitute it into the surface area of the frustum equation. So we have pi times r2 minus r1 times b, which we said was lr1 over r2 minus r1. And then plus pi times r2 times l. And from here we can reduce and simplify, and we get pi lr1 plus pi lr2. And if we factor out pi times l, we have r1 plus r2, which we know is 2 times r, where r is the average radius. And so we get pi l times 2r, or 2 pi r l. And we recognize 2 pi r as the circumference of the red circle. So we can call this circumference L. Okay, this is a result that we will keep in mind as the area for the frustum of a cone. Next, we want to consider then, in a general shape, if we don't have a solid which is a frustum of a cone, but we have a solid of revolution, we can consider a curve y equals f of x revolved around an x-axis, or perhaps in a later case revolved around the y-axis, and we can get a solid of revolution. If we want to find the volume for the solid of revolution, we can chop up the solid into cylindrical shells or cross sections, and we can use the techniques from chapter 7. But in the case of coming up with the surface area, we would still slice perpendicular to the revolution axis, and we would get these approximating bands, like wristbands. The only thing is, these wristbands do not have straight across horizontal edges. In fact, they don't even have straight across slant edges, because the curve is not straight in general. And what we are going to do is approximate the slant edge with a straight line segment so that it looks like a frustum of a cone if we turn this band on its side. Now, of course, the actual side of the band may be curved. And so as we take thinner and thinner slices, we will get more and more straight edges for the frustum of the cone. And therefore, we can approximate the band with the surface area as the surface area for the frustum of a cone. So the typical band is a thin frustum of a cone with an average radius of r and a lateral side length of delta s. As the solid is sliced into more and more bands, delta s approximates or approaches ds, and the surface area of the band can be given by surface area equal to the integral of a little bit of surface area, which is equal to a measurable amount of circumference times ds accumulated, or the integral of a little bit of circumference times slant side. So recall, we had just found that the surface area of a frustum of a cone is equal to circumference times the slant length, or 2 pi r, where r is the average radius, times the slant length. So we are saying that if we want to come up with the area of a typical approximating band, that surface area is equal to the integral of a little bit of surface area. Surface area of what? Surface area of a frustum of a cone. So the frustum will have a typical radius, or an average radius, of r, and that average radius will produce a circumference, which is equal to 2 pi r. And then we multiply by the slant length. In this case, the slant length is delta s. And as we take thinner and thinner slices, the slant side of each band, delta s, gets more and more straight and is approximated by a little bit of slant side. So we are going to choose a measurable amount of circumference multiplied by a little bit of slant side, as opposed to dc times s. And so the circumference gets replaced with 2 pi r, we multiply by ds, and we integrate. In exercise 1, we want to write the surface area formula in terms of x and then y. And we want to discuss under which circumstances you could or must use each formula. Well, if we go back to our previous picture, and we have our curve, and we revolve it, and we come up with a typical band. A typical approximating band would look like this. And we would have a typical point at the average radius, or at the center, midpoint of this, P, which is located at x comma y. We still have that the curve is y equals f of x. And we know that we have a radius, in this case, based on revolving around the x-axis, of some change in y. So we would say that the surface area is equal to the integral of a little bit of surface area, which is going to be the integral of circumference times a little bit of slant side, which in this case is going to be the integral of 2 pi r times ds. If we're revolving, as we showed here, around the x-axis, then we have that our radius is equal to a change in y, and revolving around the x-axis, which of course is the equation y equal to 0, says that we have the y-coordinate called f of x, y top minus y bottom, is going to be f of x minus 0, which is f of x. And therefore, we are choosing to integrate with respect to x, and so we have to come up with ds in terms of x. Going back to 9.3, we saw that ds could be written as 1 plus f prime of x, or dy by dx, all squared, and then multiplied by dx. And this came about from the Pythagorean theorem, if you recall. We had a triangle with a slant side ds having a horizontal length dx and a vertical length of dy, and relating ds squared equal to dx squared plus dy squared. So making this substitution and coming up with bounds of integration, we would probably be integrating from some starting x-coordinate to some final x-coordinate. Let's call them a and b. So we would get the integral from a to b of 2 pi, which are constants I will take in front of the integral, times the radius, which is f of x minus 0, as we are revolving around the x-axis. And so we have f of x times the integral of 1 plus f prime of x quantity all squared, and then times dx. So we could use this as long as we can actually isolate y and solve the equation in terms of x. So if that's the case, we would choose ds equal to this expression. And we do have to be careful that this f of x represents the radius, which is y top minus y bottom. Now let's say that we couldn't actually isolate y from the equation and we had to isolate x. If that's the case, then we would have to say x is equal to some inverse function of y, some inverse of x. Let's call, f inverse of y, and let's call f inverse g. So if that's the case, we would have to rewrite ds in terms of y. So we could say that the surface area formula is given by the integral of a little bit of surface area, which is circumference times a little bit of slant side. And in this case, the slant side ds has to be in terms of y, because we are saying in order to express in terms of y, we rewrite this. And so we get 1 plus dx by dy, all squared, and then multiplied by dy outside of the square root. So the integral is going to become some y-coordinate for point A and point B on the curve. And I'm actually going to change these from being A and B to being x subscript A and x subscript B. And so now we have 2 pi times the integral from y subscript A to y subscript B. And we see that the radius is still a change in y, in which case it's going to be the y-coordinate called y minus 0, which is what the y-coordinate on the x-axis is. And so now we have y times the square root of 1 plus dx by dy, which is actually g prime of y. And don't forget that g is f inverse. So we could express the surface area integral, or the integral for surface area, in terms of y as follows. So the difference here is we have to be really clear on the algebra. If we can write the blue equation in terms of y, isolating for y in terms of x, then we can integrate with respect to x. And then this radius, which is a change in y, or a change in height, from the axis of the horizontal axis of revolution, would be f of x minus 0. However, if we cannot isolate for y, and we can only isolate for x, then we have to use an equation, an integral in terms of y. And in that case, we are going to say that the radius is the y top minus y bottom, which is y minus 0, which is just y. And we have to rewrite the ds expression in terms of y. And this is review from 9.3. Ultimately, it boils down to the algebra who we can isolate for, either y, and therefore the integral is in terms of x, or we can isolate for x, and therefore the integral is in terms of y. Notice that for both of these integrals, we only have one horizontal axis of revolution. We haven't considered yet revolving around the y-axis. So for parts C and D of this question, I would like you to consider revolving around the y-axis and coming up with an integral in terms of x and an integral in terms of y. In exercise 2, let's just discuss. The textbook says that surface area is equal to 2 pi y ds, or the integral of 2 pi x ds, where ds is either the distance in terms of dx or in terms of dy. Question asks, are these formulas always true? If not, what special cases are these formulas? Well, when we break it apart and we look at surface area equal to the integral of a little bit of surface area equal to the integral of circumference times a little bit of ds, we can see that circumference is either being called 2 pi y or 2 pi x. So under what circumstance is 2 pi y the same as 2 pi r? Well, what we're saying here is that the radius has to equal y, which is really y minus 0. And if that's the case, we have y top minus y bottom. We're saying that y bottom is equal to 0, and therefore we are revolving about the x-axis. So we do have to be very careful. This is a special case formula if we are revolving around the x-axis. What if we were revolving around some other horizontal line, say y equal to -1? Then this expression would not be true because the radius would be y minus -1, and we would have to have 2 pi times y plus 1 instead of 2 pi times y. Similarly, in the second case, if we have 2 pi x in place of 2 pi r, what we're saying is that the radius is equal to x, which would be x minus 0, and so for x right minus x left, we are saying that x left is equal to 0, which could be the y-axis. So again, these are two special case scenarios for revolving purely around the x-axis or the y-axis, and you'd be better to go to the more general surface area is equal to the integral of 2 pi r times ds, and then decide whether it is easier algebraically to isolate for x or for y, and therefore to express the integral in terms of y or x. You can then use your choice for ds in terms of either x or y, and you can express r in terms of x or y as you need. But you can also consider that r will be a change in y or a change in x, which allows you to consider a different non-x or y axis of revolution. In number 3, let's actually do a practical application. Determine the lateral surface area of the solid generated by revolving the curve y equals x squared between the points 1, 1 to 2, 4 about the x-axis. Well, let's actually do a setup where we revolve not around the x-axis but around the line y equals -1, just to be really clear, and we will set up. So we'll do two cases. We'll determine revolving around the x-axis, but we will do a setup of the integral revolving around the y equal to -1 axis. So I will do the setup, and you can determine the integral for the x-axis at a later point. Okay, to set up the surface area, let's actually draw a picture first. We have the parabola y equals x squared, and we are going to choose a section of that from 1, 1 to 2, 4, and we are going to revolve around the line y equals -1. And so we are going to get our solid of revolution, and we are going to imagine chopping it up to get some approximating bands of surface area. Okay, so we have our surface area band, which approximates a frustum of a cone. And we know that the frustum of a cone has a surface area of 2 pi r times the lateral side length, which in this case is delta s. But we are going to choose this in such a small width that the curvature here, we actually have a curvature, is going to be approximated by a straight slant side as we take thinner and thinner slices, and therefore we're going to get a little bit of surface area, which is going to equal 2 pi r times a little bit of slant side. And therefore the surface area will equal the integral of a little bit of surface area. So we have to decide whether we want to integrate with respect to x or to y. And we're going to take our typical point here. Let's call it point P, x comma y, and we can have that point P along here, which produces a circumference of 2 pi r. Now we know that the radius here is going to be a change in y. So our radius is a change in y, so we have y top minus y bottom. And y top in this case is, we could either call it y or we could express it in terms of x. But y bottom cannot be expressed in terms of x, so we are going to have to change y top into x squared. So this is going to be x squared minus negative 1, and so we get the radius is x squared plus 1. So that tells us to integrate with respect to x, and we change our ds expression to the version in terms of x. So we get 1 plus f prime of x quantity all squared under the square root and then times dx. Well, we know that f of x is equal to x squared, so the derivative is 2x. So we get 1 plus 2x all squared under the square root and times dx. And we substitute in, we have to put in our bounds for x. So the surface area is equal to the 2 pi times the integral from x equals 1 to x equals 2 of the radius, which is x squared plus 1, multiplied by 1 plus, we can expand this and get 4x squared, and then times dx. So this is a setup. It may not be easy or even practical or possible to integrate by hand. So part of the questions that you will be seeing are to simply set up a surface area integral. However, you can attempt the blue version to determine the lateral surface area if we're revolving again instead of around y equals negative 1 around the x-axis. In number 4, we want to show that the surface area formula for the parametrized curve x equal to f of t and y equal to g of t is given by the following expression. We know that r of t is going to be either r a function of y of time or r a function of x of time, depending on the axis of revolution and the algebra of the curve. Well, we can start off with a shape if we want. We don't know if the curve is going to be revolved around x-axis, y-axis, or some other horizontal or vertical line. But if we do that, we can come up with a typical approximating band. We do know that we have the x-axis and the y-axis. And for our typical approximating band, we have the typical point P, which is P of x, P at x comma y, where x is f at t and y is g of t. So according to this picture, we are going to have a radius, and the radius, according to this picture, is delta y, which is going to be y top minus y bottom. Now, I don't really want to specify whether this is going to be 0 for y bottom because I'm not going to assume that we are revolving around the x-axis. Notice here that we are simply leaving this radius as r as a function of some time. And so whatever we choose to do, represent in terms of the x-coordinate or the y-coordinate first, we're going to see that this is a radius function of time. We know that we're going to take some initial point, let's call it point A, and go to some final point to get the surface area. And this is x at time A, y at time A. And this is x at time B, comma, y at time B. And so we can say that the surface area is equal to 2 pi times the integral of the radius times ds. The bounds of integration are going to be from time A to time B. The radius, we don't know exactly without knowing the algebra and the axis of revolution, so we can leave it for now as r of t. And we know that we want to express ds in terms of dt. So remembering that ds squared was equal to dx squared plus dy squared, and then we can divide both sides or multiply top and bottom of the right-hand side by dt squared. Then we can take the square root of both sides, and that's going to give us a dt on the outside of the square root, and leaves us with dx by dt all squared plus dy by dt all squared under the square root. And so that will be our dx. I'm just going to move that a little bit lower. Sorry, this will be our ds. And so we are going to refer to dx by dt as either that or f prime of t. I think here I'll call it f prime of t. Quantity squared plus g prime of t, quantity squared, all under the square root, and then times dt. So again, depending on the algebra, whether we can isolate for x or y, and interpret it first of all as a dx or a dy before interpreting it as dt, and then secondly, what our axis of revolution is will impact the r of t expression. But this is the basic idea about replacing ds in terms of dt and using t bounds of integration and a t function for the radius. For the last question, we want to use integrals to show that the surface area of a sphere of radius r is given by 4 pi r squared. So when we consider our sphere, we want to see it as a solid of revolution. So the first thing we need to do is put it in a coordinate system. And I'm going to place the center of the sphere at the origin. And I'm only going to focus on the top half of the sphere, find its surface area, and then double it by symmetry. And furthermore, I'm going to see that if I have in profile, I have a circle here of center 0, 0 and radius of r. And so I have the equation of the sphere in quadrant 1. Well, I have the entire boundary curve given by x squared plus y squared equal to r squared, and therefore y in quadrant 1 is going to be the square root of r squared minus x squared for x contained from 0 to r. So if we revolve that boundary curve, I think I'll highlight it so we can see it a bit better. If we revolve that boundary curve about the y-axis, then we will generate a shell of the top half or of the hemisphere. So we'll generate a hemisphere. By doubling the surface area integral, we will come up with the surface area for the full sphere. So going back to basics, we know that surface area is equal to the integral of a little bit of surface area. And in this case, we're going to have the integral of a measurable amount of circumference times a little bit of slant side. So we can take a look at a typical approximating band, which is only going to go to the x-axis because I'm only going to take the top half of the curve. So I have a typical point here, P, with coordinates x comma y, and I know that my radius is going to be not the radius of the sphere, but the radius of the approximating band. It's a little hard to tell, but my approximating band comes back around here, and I'm not really taking into consideration the bottom half of the sphere at all. So when I take a look at this, we come up with a radius, which is a change in y. So we have radius, and I'm going to use a capital. I'm just going to write the word. I'm going to write radius of the band, because I do not want to confuse with the lowercase r that I'm using for the radius of the sphere. The radius of the band is a change in y, which is y top minus y bottom, and y top is given by the boundary curve. And y bottom is given by the x-axis, where y is equal to 0. And so we can go over here and substitute in. We have 2 pi times the integral from x is 0 to r. We have that the radius is in terms of x, and therefore we need to express ds in terms of x, which is going to be 1 plus dy by dx all squared times dx. And this is getting a bit messy, so I think I'm going to rewrite this on the next page. So we get surface area is equal to 2 pi times the integral from 0 to r of the radius we said, which was the change in y, square root of r squared minus x squared, multiplied by ds in terms of x, which is the square root of 1 plus f prime of x, quantity squared, times dx. And so we should go back and we can work out what y prime is going to be. Y prime is going to be 1 over 2 times the square root of r squared minus x squared times negative 2x. And we can reduce this to give us negative x over square root of r squared minus x squared. So we have to square that to put it inside the surface area integral. Now this is actually the surface area for a hemisphere, so I'm going to do double that to get the surface area of the full sphere. And so that's going to make the constant in front 4 pi times the integral from 0 to r. And let's make our substitution for f prime of x, and then square it. Once we square it, we're going to get positive, and the numerator was x and the denominator was square root of stuff. So we're going to get x squared over r squared minus x squared, and then times dx. So we get 4 pi times the definite integral from 0 to r. We can make one big square root out of all of this and multiply the products, or the factors. So r squared minus x squared times 1 is going to give r squared minus x squared. And then r squared minus x squared times something over itself. This will reduce with this, and we are left with plus x squared. And then times dx. And so we have that r squared is a positive number, r is a positive number, and its square root is r. So we can take the r outside to get 4 pi r, and then we have times the integral from 0 to r dx. This is going to give us 4 pi r times x evaluated from 0 to r, which is going to give us 4 pi r squared as desired. Well, this concludes section 9.4, area of a surface of revolution. Please complete the accompanying handouts and prepare a list of clarifying questions about the lecture. That's all for now.